So before we subject this new series to any test, one test or another, let's drag out the order thermometer for a second and see if we can't at least develop some kind of intuition for where this series belongs. In particular, here's a sort of a use of the order thermometer that I want to stress today, because it's going to help us to decide when we should maybe go directly for the ratio test and when maybe we shouldn't go directly for the ratio test and we're going to have to do some kind of a comparison. So the ratio test, which isn't a part of 10.4, but I wanted to talk about it now anyway. The ratio test is extremely useful for series that have factorial or superpower growth, because the ratio of a factorial or a superpower series tends to equal 0. And that's a conclusive result, right? Because if the ratio is equal to 0, then in particular, it's less than 1, and we're going to get convergence. So up here, the ratio test is a good idea. So when you see that your series is dominated by factorials or dominated by superpower terms, you're probably going to end up going for the ratio test. And the same is true for exponentially dominated series. In the exponential regime, the ratio test tends to pull out a ratio, an asymptotic ratio, which is between 0 and 1, strictly. And again, being between 0 and 1 is a conclusive test for the ratio test. And so if we see that our series is dominated by exponential geometric factors, or terms, then we're probably going to go for the ratio test again. This is why the ratio test is so useful, is that all of the series in these parts of the thermometer here yield really well to the ratio test. The ratio test gives you something conclusive. The only place the ratio test does not give you something conclusive is for all of the series below this line. So those series that are dominated by logarithmic behavior or by polynomial behavior tend to give you a ratio of 1. And a ratio of 1 in the ratio test is inconclusive. So it's in this regime over here that we tend to use comparisons. Or in the worst case scenario, depending on your perspective, we might use integrals over here. So the ratio test tends to be the most useful when you can find exponential, factorial, or superpower terms in your infinite series. In fact, for superpowers, which we haven't done much with, superpowers we tend to go, instead of for the ratio test, we tend to go for the root test. And we won't cover the root test on this exam, but we can talk about it if you'd like to. So looking at our example here, if this were not a part of section 10.4, which test do you think would be the most appropriate, or would be the quickest, let me put it that way, the least painful test for assessing the convergence or divergence of this series? Ratio test. Because where does it look like this series belongs? Well, superpowers are n to the n power, so that's not quite what we have here. Instead, we have a 5 to the n and we have a 3 to the n, each of which belongs in the exponential category. So the 5 to the n is somewhere in here, the 3 to the n is somewhere in here. But notably, we definitely don't have any factors that are just polynomial. So we don't have any factors that belong down here in the logarithmic or the polynomial regime. We only have stuff that looks geometric, exponential. So if this were not a part of 10.4, we would probably go directly for the ratio test and just bypass the idea of a comparison. But because this is a part of 10.4, we owe it to ourselves, I think, to try making a comparison, because that's probably what the authors wanted here. Obviously, I don't care in the long run, unless I tell you specifically to use one test or another, which I usually don't do. Ultimately, it doesn't matter to me which of the tests you go for, as long as you apply the test honestly and appropriately and make the correct conclusion from it. So let's think in a comparison, from a comparison standpoint. What infinite series could we compare this 1 over 5 to the n minus 3 to the n to? 1 over 5 to the n? So this is a part of the use of the comparison test that I wanted to stress today, is that what makes a smart choice for a comparison is to look in your numerator and look in your denominator and choose from each the term or the factor which is the highest order on the order thermometer, and just take that term out. Pull it out and use it for your comparison. So looking on the order thermometer, 5 to the n and 3 to the n both belong to the exponential category, but 5 to the n has a higher common ratio than 3 to the n does. So 5 to the n is at least a little bit further to the right in here. And so we expect that in the denominator, between 5 to the n and 3 to the n, it's the 5 to the n that's setting the pace. It's wearing the pants in that relationship. Upstairs, meanwhile, we only have a 1, and so we have to keep that 1. And so our goal here would then be to compare these two series, one to another. And the other reason that this is a good comparison is, what do we know about the infinite series summation of 1 over 5 to the n? What does it do? It converges, because why? It's a geometric series, and what's its common ratio? 1 over 5. Right. Geometric with a ratio of 1/5. And because that ratio is less than 1, this is a convergent geometric series. So then our goal is going to be to conclude that our unknown series is either term by term smaller than this, if we're doing a direct comparison, or if we decide to do a limit comparison, an asymptotic comparison, we need to conclude that these terms approach 0 at a higher order, or at least the same order compared to 1 over 5 to the n. So there's our target. So which would you rather try here, a direct comparison or a limit comparison? I'm going to claim that one of them actually doesn't work the way that we would want it to, namely the direct comparison. Can anyone see why the direct comparison between these two series doesn't work? Look at the difference between the two. If I subtract 3 to the n from the denominator on the left, that makes the denominator of this left-hand side smaller. But if the denominator is smaller, that means that the fraction is bigger. And so the direct comparison between these two series would look like that. The series on the left is at least as large as the value of the series on the right. But since the series on the right is convergent, saying that our unknown series is bigger than something convergent is not a good comparison. Right? Because being bigger than something which is finite could still be finite, but it could also be infinite. So we're going to, I think, reject the direct comparison here and try for the limit comparison instead. And this is a good place to remind you how limit comparisons work. How does a limit comparison work? What do I have to set up here? Divide. So I take my unknown series and then put a big division sign under it, and then put the terms of my known series, 1 over 5 to the n, downstairs. And again, my goal is to figure out between these two sequences, because both of these sequences have the same limit. They both have the same goal. They're racing to the same finish line. Both of these sequences are going to 0. And so our goal then is to figure out which one of them gets there ahead of which at a higher order. Because that's the one where the 0 is going to be preserved in this fraction, and we'll be able to conclude which one is getting to 0 faster than which. So L'Hopital's referee says, let's find the limit of this ratio as n goes to infinity. How do we do it? We're going to need a derivative, but before we do that, we should probably simplify. Algebra before calculus, right? So flippity-do on this compound fraction. And we end up with that 5 to the n. Whoops. 5 to the n ends up upstairs in the numerator. And 5 to the n minus 3 to the n ends up downstairs in the denominator. And now would be an okay time for the derivative in L'Hopital's rule. The problem is, if I look ahead to what's going to happen in L'Hopital's rule, if we start taking derivatives, what's the derivative of 5 to the n? Times ln 5, right. And then downstairs we would get a 5 to the n times ln 5, and a 3 to the n times ln 3. And if we took the derivative again, we would get that squared, kicking out. If we took the derivative again, we would get third powers on those natural logs of 5 and 3, etc., etc., etc. So at no point is L'Hopital's rule going to make this not an indeterminate form anymore. These are still, the numerator and denominator are still both going to infinity, no matter how many times we take their derivatives. So instead of L'Hopital, to evaluate this limit, let's opt for some algebra. Here's where we can use the fact that we chose our simple series, 5 to 1 over 5 to the n, to have one of the same terms as our unknown series, 1 over 5 to the n minus 3 to the n. Let's leverage that and simplify this fraction by dividing its numerator and its denominator by 5 to the n. So here's our move. Divide downstairs by 5 to the n, divide upstairs by 5 to the n. And that's a good move, because while the numerator used to go to infinity, as n goes to infinity, our new numerator, 5 to the n divided by 5 to the n, is 1, which does not go to infinity, as n goes to infinity. And now comes the fun part. What do we get in our denominator? 5 to the n divided by 5 to the n, minus 3 to the n over 5 to the n, which I'm just going to write like that for the moment. 3 to the n over 5 to the n. And then we're still tasked with taking the limit of this as n tends to infinity. Why is it easier to see what this limit does now than it was before?
There's no variables on the top.
There's no variables on the top. Our n's are all in the denominator. That's the first observation. So this is no longer an indeterminate form. And all we have to do is answer what happens to 3 to the n over 5 to the n as n goes to infinity. Well, numerator and denominator there both have a power of n. So let's pull out that power of n. And now we can ask ourselves, what happens to the number 3/5 when I raise it to successively higher powers? It gets smaller and smaller. In fact, what is the limit of 3/5 to the n as n goes to infinity? This is something you could do with a calculator. So 3/5 to the n as n goes to infinity becomes 0. And so what is this limit in total? 1 over 1 minus 0. Yeah. So we just performed a limit comparison test, and we got an answer of 1. So what does that tell us about the relative orders at which these two sequences, 1 over 5 to the n and 1 over 5 to the n minus 3 to the n, approach 0? It's a tie, exactly. Both sequences get to 0 at the same order because of that 1. Because our limit of the quotient was finite and non-zero. So how do we make a conclusion? Yes, that the original series, summation of 1 over 5 to the n minus 3 to the n, has the same order as 1 over 5 to the n. And we happen to know that 1 over 5 to the n is convergent, a convergent series. Summation 1 over 5 to the n. And therefore, our original series must be convergent. By the way, is that convergent absolutely or convergent conditionally? Absolutely. How come?
It's not alternating.
Because it's not an alternating series. All of its terms are positive, so that if we came in here and we took the absolute value of everything, we wouldn't get anything different. When I take the absolute values of all the terms, we get the same series. So if the sum of the absolute values converges, then our series converges absolutely. That's where the name comes from.